This is going to be a talk about research ships, both at Scripps and nationally, as the essential tools for what we do, which is science at sea. I'm not going to talk about any one piece of oceanographic research, but I'll give some examples and illustrations of quite a number of them. The focus is really on research ships as the key means by which scientists do get out to sea and carry on their observations and measurements. There's a tremendous variety in that, and I think that when it comes down to is that ships ought to be viewed as the essential ingredient, the sine qua non facility for doing oceanography, rather like telescopes for the astronomers, which is the origin of the title slide. Let's get right into it. This is a list of a number of previous talks in this series, and I present it not for you to read the whole thing, but just to look at the variety of what's been presented here previously. And I've indicated in yellow talks on subjects that have been absolutely dependent in one way or another on the use of research vessels, either to go and do the actual experiment that underlay the talk, or to collect measurements and samples that were bundled together somehow into the research project that's indicated there. And obviously not everything that's done here at Scripps falls into the yellow category, but a great deal of what we do does, as you can see just by scanning that list. Don't worry about reading the individual words, but just look at the fact that there's a lot of yellow on that slide. We're going to take a look at some of these in a little more detail. Here's a list of 5 of them that I'll talk about briefly, selected to be a kind of a smorgasbord across the ocean sciences. So, for example, we lead off with the talk that Dan Rudnick gave here on fronts and eddies, the weather of the oceans, which involved very precise navigation and towing behind the ship of this instrument called Seesaw. Signals from the sensors on this instrument come up the wire. Hello, where did my little pointer go? Come up the wire and into the ship. You can't really see it in this thing. And control signals come down into the vehicle and alter the angle of attack of the wings to make this vehicle seesaw up and down like this as it follows the ship through the ocean, thereby making a very dense set of measurements of regions of strong contrast in temperature and salinity in the upper ocean, the ocean fronts and eddies analogous to atmospheric fronts that we all know about from personal experience on land. There's a big winch involved, a very specialized winch. It has to handle cable like this that has some streamlining attachments on it so that the cable drag is manageable. And the whole affair is obviously a pretty heavy industry and pretty specialized operation that can only take place on a research vessel. A few hundred meters up and down in the upper ocean, not very deep, but good enough to get at the zones of highest contrast in the upper ocean that are affected by the atmosphere. Another talk by Wolfgang Berger, 1,000 Years of Climate Change, looking at annual signatures of climate conditions in sediment cores that were taken in a number of places, particularly in the Santa Barbara Basin. Wolfgang himself didn't take all these cores. He may not have even taken any of them for all I know. But there's certainly a library of core samples like this from ships of various institutions over a long period of time, an invaluable scientific library for research down the years. And as you'll see later on, I'll show you a little more about coring. It again is something that really depends on a capable research vessel to get it done. Donna Blackman talked about exploring an undersea mountain using the deep submersible Alvin that's operated by the Woods Hole Oceanographic Institution, which is obvious from the picture and from what you already know is utterly dependent on the mothership Atlantis. Atlantis is a sister ship of our own Roger Revelle. Mark Oman talked about shipboard acoustical observations of the daily vertical migrations of euphausids, little critters that sort of aggregate in a layer and migrate up and down in a daily cycle. And that became an important practical aspect of submarine operations in the Second World War, because these guys have little air-filled or gas-filled bladders, and in aggregate they make a fairly good acoustic reflector. So if you know something about where they are and where they're moving, you can, depending on which side you're on, you can think about hiding underneath them, or you can think about trying to work through them to find the bad guy lurking underneath. It had more than academic interest in submarine warfare. And the initial observations of these critters and the realization of what was going on, that it was in fact an acoustic signature of biological origin, was again something that was accumulated from research vessels over time at sea. John Orcutt talked about new programs in ocean observatories and networks of sensors on the seafloor using continuous presence on the seafloor to be able to measure something about events that tend to be abrupt and episodic, like volcanic eruptions or earthquakes or things of that sort. If you have an earthquake and you only then turn to measure something about it, you've missed the bus. You have to have your sensing array in place beforehand, and the only way to do that in the marine environment is to have a network of gadgets, sort of cartoon gadgets here, in place on the seafloor in parts that you're interested in, and installing and maintaining a network like this depends on capable research vessels to do it, and furthermore it's necessary to have research vessels to carry out experiments that are sort of set within the context of this. Think of this as a network of sensors that are there all the time, but there are specialized experiments that you're going to want to do from time to time that take advantage of this background of ongoing instrumentation. So again, that's just a quick glimpse at 5 projects selected from that list spanning the disciplines in ocean sciences to give you some sense of how fundamental the use of research vessels is for so much of what we do in the ocean sciences. With that as preface, a good place to begin is at the beginnings. We're going to take a little bit of a walk down the historical path here. This is the research vessel Alexander Agassiz that the institution operated from 1907 to 1917. She was 85 feet long, actually the first U.S. ship designed specifically as a research vessel. But when all is said and done, one has to admit that really what ships like this were back then were ordinary ships with a fairly rudimentary stash of instrumentation and observing capability. It was pretty much the case of wooden ships and iron men, and in fact they were all men at that juncture. Let's fast forward a couple of decades to the 1930s and beyond. This is the research vessel E.W. Scripps. 94 feet long. The second from the left, the tallest guy in the group as usual, is Roger Revelle. And this was a ship that, that came to the institution from Robert Scripps, who obtained it and provided it to the institution in December of 1937, roughly a month after an accident and fire aboard the previous vessel named Scripps took place at her moorings at the San Diego Yacht Club. That fire wrecked the vessel, Scripps, and it also unfortunately killed the cook and injured the captain, who were both living aboard at the same time. And so this ship was, as I said, obtained and provided to the institution in the wake of that tragedy, and represented some of the first seagoing work that Roger himself participated in. His widow, Ellen, tells a wonderful story about the fact that when Roger went out for his first trip, one-day trip, just in the local waters, the tradition around here was that the new boy had to cook the lunch for everybody aboard. So that fell to Roger, and he still thought it was one of the best days of his whole life. And I think it's fair to say that his subsequent drive to get this institution out to sea and making really meaningful observations in the open ocean is a huge part of what's made Scripps the leading institution that it is today. Let's see, we're going to jump forward another period of time to the current era. This is our marine facility down in Point Loma. Many of you have probably seen it from the water or elsewhere. The Nimitz Marine Facility, it's named for Admiral Nimitz of World War II fame, but less well known is the fact that he was also a regent of the university between 1948 and 56, and in fact organized the naval ROTC program at the Berkeley campus in the 1920s. We Scripps operate 4 of the UNOLS vessels that Cheryl mentioned. I'll say a little more about UNOLS later on, this confederation, if you will, of oceanographic institutions. And they're pictured here on a rare occasion when they're all in port. Generally speaking, they're out at sea working, but there's the Melville, there's the Sproul, there's the Revelle, and there's the New Horizon. And this is the research platform, not a proper ship, Flip. This collection of ships can do everything from small local projects to projects that take ships all over the world. It just depends on the particular project and its ship needs in terms of capability and size and duration and so forth. You don't take a big ship to do a small project, but we have a variety of sizes here. They handle all kinds of oceanographic sciences. And as members of this UNOLS consortium, there's a kind of a scheduling optimization that takes place across the national fleet, not just the Scripps fleet, whereby scientists from Institution A can go to sea and do his or her work on a ship from Institution B, if that makes sense in terms of the location and timing of the ship. So you'll frequently find people from Scripps doing work in the Atlantic on Woods Hole ships, and conversely. And at the national level, it makes for a much more efficient and cost-effective operation. Moving through this a little more, a few more facts about the fleet as a whole. The two big ships, Melville and Revell, are in fact owned by the U.S. Navy. We operate them under an agreement with the Navy, but the Navy retains title. That's a commonplace of the post-war era for the American academic fleet as a whole, and it's worked extraordinarily well. Sproul and New Horizon, the two smaller ships, are owned by the university. You can think of this place down here on Point Loma, just opposite the end of the island over here, as a kind of a Houston or Cape Canaveral, if you will, for our shuttles that go to inner space instead of outer space. They're like the shuttles in the sense that there's some combination of laboratory and home and life support system all in one. And they also have something in common with the shuttles in that they go to dangerous places where you have to do things precisely and safely or bad things happen. And so far, so good. We've had a remarkable safety record not only at Scripps but in the UNOLS fleet generally across the country. It's not to say that nothing bad has happened, but the frequency has been fortunately very low. These guys are going to remain, I believe, our primary means of observing the ocean, both now and in the future, at least as far ahead as I can see. That's not to say that there aren't other ways of getting important, indeed, information that you couldn't get any other way from the ocean. Satellites, unattended instruments, drifting instrumentation, and on and on. There's quite a long list. But I think it remains true that ships are going to still be primary in this enterprise of observing the real ocean, both for making kinds of measurements that nothing else can possibly do and for deploying and tending some of these fleets of other instruments that don't have people along with them. There's no end in sight that I can see of the need for a ship with a capable laboratory and smart people aboard to go out and do an awful lot of what remains to be done in the ocean sciences. So I think it's safer to think of the new kinds of instrumentation not as something that's going to elbow ships aside and into the museum shelves, but rather as techniques that are going to augment what the ships do and vastly improve our ability to observe and therefore to understand what's actually going on in that remarkable system out there that's so opaque when we look at it from the beach. We'll take a quick tour of the individual ships in the Scripps fleet. Start with the smallest one. This is the research vessel Robert Gordon Sproul, named for former president of the University of California. In all these cases, I've listed sort of, principal particulars for the ship alongside here. So you can see something about the size and range and how many people she can carry and so forth. We got to Sproul at a very favorable price back in 1984 in a lull in the offshore oil industry, and Sproul was a small offshore oil supply vessel. And she served extraordinarily well in the years since. We've modified her considerably here at Scripps to do science instead of tending oil rigs, and she's done amazing amounts of work, primarily in local waters, although she's been as far afield as Baja and the Pacific Northwest. Typically a few-day kind of trip in and out of San Diego. This is the ship where an awful lot of Scripps graduate students have cut their eye teeth and really learned the ropes about how to organize an actual research project at sea and get things done and deal with problems as they arise in real time. Next up in the size range is the New Horizon, built new in 1978. Substantial midlife refit of the vessel a few years ago, again owned by the university. This ship has been the backbone, among other things, of the California Cooperative Ocean Fisheries investigations. As many of you know, this is a 50-some-odd year series of repeated observations of the physics and chemistry and marine ecology off in the California Current region here. It was set in motion over 50 years ago in an attempt to understand at a fundamental level the kinds of changes going on in the California Current region that had, among other things, given rise to the collapse of the California sardine industry shortly after the end of World War II. That fishery, the California sardines, when it was at its peak. This is the fishery of Cannery Row fame, that fishery was the biggest in the world in terms of weight of fish landed, and then it cratered. And the question was why? The answer, I think, is unfolding as some combination of overfishing and natural variability in the system. But the only way to drill down to those kinds of answers is to have repeated observations in time, and that's what Cal Coffey has done superbly well for over half a century, and this ship has been, I think, part of the backbone of that program for as long as she's been in service. This is the only case in which the state and the university have funded a new research vessel for Scripps. I hope it's not the last, but it's the only one so far. Next up in size is the Melville, one of the two Navy ships that we operate. Built originally back in 1969, but in 1992, she was cut in half about here and 34 feet added to it. This is the long version that's in the picture. Still going strong and doing tremendous amounts of global scale ocean science in the current era. And finally, our newest vessel, Roger Revelle, some particulars here listed alongside the photographs, built by the Navy at Halter Marine down in Pascagoula, Mississippi. I don't know what the state of that shipyard is. I know that Senator Lott's house just down the road got pretty well leveled, but I don't know what the shipyard is like. I've been unable to find out thus far. The Navy owns the ship. Scripps had to compete to operate this ship. There was a proposal put out to the world for various institutions to compete for that honor. We won it. And it's a global ship that can go essentially anywhere that isn't covered by ice and do whatever sort of oceanography you wish. There's a few more facts about the Revelle, just to give you some context: length, speed, et cetera, et cetera. Nowadays we have some more advanced things than in the vessels that we saw with Roger Revelle. There's an audio-video network around the ship. There's almost continuous connectivity to the internet through satellites. There's in-room computer connections. You can literally sit in your cabin and check your email if you're so inclined. Some of us are not inclined to do that when we're at sea, but it can be done. It's air-conditioned throughout. And Roger doesn't have to cook the lunch anymore. We have regular cooks and 3 meals a day, and your biggest problem out there, I think, is to refrain from gaining too much weight. In terms of the scale of this operation, I thought a few of these numbers might be of interest to some of you. These are taken from the year 2003, so they're a little bit outdated, but it was a little over $5 million to operate the ship in that year. That's the all-in cost. That's paying the crew and the insurance and the fuel and the maintenance and all of that. Works out to about $19,000 a day being computed as 272 of them in the year. It's what we call an operating day. That is a day the ship's actually out on the ocean or away from San Diego. Days in San Diego don't count. This is a breakdown of how the costs parcel out. Most of it obviously is to do with people, either in the crew or support people ashore, and then the rest of it is things like repairs and fuel and other. And this one for fuel is going up faster than I can keep track of at the current era. Just because we have 3 wonderful meals a day and all these creature comforts, I don't want you to get the idea that it's all just a walk in the park out there. There's still an aspect of iron men and now iron women involved in doing oceanography at sea. There's one example. This is in the Sea of Japan in the winter of 2000. And this black tower on the bow of the ship is black up here and it's white down here, but that's not a two-tone paint job, that's ice from the freezing spray that comes over the bow. And unlike an airplane where you can de-ice it on the ground and then get up into dry air aloft and you're set, you don't get up aloft, you have to keep chipping the ice. Otherwise the ship gets top heavy and capsizes, so this is an important job. And yet you still got to carry on scientific work in the midst of all this. There's a so-called CTD, conductivity temperature depth sounding apparatus that's getting ready to go in the water. It probably weighs a few thousand pounds when these sample bottles are full of water. And it's being lowered on a winch wire that you see here. And if you look carefully at this picture, you can see there's still plenty of ice around, so that handling this thing safely on a rolling deck in those conditions is not something for rank amateurs. It has to be done carefully or somebody gets hurt. Here's another picture just to give you a sense of life on the ocean. If you can work out the geometry of the ship and the horizon, I think it pretty well tells the story. It's surprising, isn't it? It doesn't look so terribly dramatic on the sea surface, but this is the Melville, the other big ship. And you can work out the angle just by staring at the horizon and the foremast. And they were rocking and rolling down the road on that one. Over time, about the last half century, Scripps ships have sailed well over 6 million nautical miles. I don't have the most recent count in my head at the moment. And these tracks give you some sense of where we've been. Obviously, there's a concentration of effort in the region of the west coast of the Americas, but they've been all over the world at one time or another. There's no ice-free ocean that you can see on here where we haven't been at some stage of the game. And I just put that up there as an indicator of the kind of global reach of what it is that these ships do and have done over time. I'm going to walk you through an expedition that recently took place on the Melville. The ship went completely around the world in just over 2 years, as you can see here from the legend on this picture. That turns out to have been the longest time ever for any Scripps ship away from San Diego. And so as kind of a record holder in that regard, it makes an interesting sequence to walk you through some of the variety of what these ships do and how Program A dovetails with Program B as the ship marches its way around its track. So we'll start off. And the other panels will look a lot like this. They'll show you the name of the scientist or scientists who were in charge of the various operations. As you'll see, they're not all from Scripps by a long shot. Klein was from Duke, Fisher was from UC Santa Cruz. Dates and ports of call, if you're interested, are up here, and a thumbnail description of what they were up to in italics here. And the red track, which we'll advance as we go, shows you where they went in this particular segment. In this case, this first leg for Klein and Fisher was a study of marine geology and seafloor properties off the coast of Central America and on part of this mid-ocean ridge system and through here. Next up was Bob Weller from Woods Hole, who sailed from Puerto Caldera in Costa Rica to Arica in Chile on this dog leg, with his principal operation being right here at the corner to replace and serve a large meteorological and oceanographic buoy for ongoing measurements of near-surface ocean and marine meteorological properties. This is a fairly heavy industry operation, so I'm going to show you a few pictures of how this actually proceeds at sea to convince you that nothing other than a capable research vessel could handle it. You start by putting the surface buoy into the water. There are two of them shown here, but this one's getting ready to go, I think, or else this one's coming out and this one's going to go in. In any event, they're identical. They carry the meteorological instruments. Here's some anemometers up here and sensors for sea surface temperature and so forth in the hull of the buoy, and they also are flotation for the mooring that's going to follow suit. This whole thing is going to be moored to the bottom of the ocean in 3-odd miles of ocean depth. Next, there's a whole string of instruments that are made up into the mooring line in series. Here's a current meter here and some other things here that have got shots of cable of selected length so that you'll have a whole string of these gadgets positioned at desired depths in the ocean when the affair is fully deployed. Here's one of them getting ready to go into the water. This is a current meter with its electronics package and data recording hardware here, and the propellers that sense the current speed shown here. Down nearer the seafloor is this string of glass spheres inside plastic hard hats. The plastic doesn't do anything to protect from the pressure. It just keeps the spheres from getting shattered if they happen to bang against something during the operation. But the glass spheres themselves are the flotation. Surprisingly, glass is tremendously strong under compression, so it makes a wonderful deep sea flotation device. And these are just hollow spheres, actually two hemispheres that are sealed together. And it's the canonical device for deep ocean flotation. There's very little else that can take that kind of pressure and not break. And the ship has been steaming ahead. The ship is over here somewhere at this point, gradually letting all this stuff string out behind the vessel. And with a good deal of forward planning, the ship will be right over the desired spot when it's time to drop the anchor and anchor this whole affair. There's the anchor getting ready to go over the side. It's a stack of used railroad wheels. I think there's about 6 of them in here. It weighs a few tons. and it'll get tipped up and dumped into the water right there. And if all goes well, that mooring will settle out with the anchor on the bottom and the big yellow buoy on the top and the instruments at the desired depth in between, and it'll stay there for 6 months or a year or something like that until they come back and service it the next time. Next leg was Don Forsyth from Brown University out to here and back into Valparaiso, studying things about volcanism and fine structure of gravity on the seafloor in this region. He made heavy use of an instrument shown in this cartoon, so-called multi-beam sonar that maps the seafloor not just directly under the vessel, a sort of old-fashioned classical way of pinging down and getting an echo back and tells you the depth underneath the vessel, but as this cartoon indicates, with an array of acoustic devices built into the hull of the ship, it can sample a whole strip of seafloor quite some distance out to either side of the vessel, probably an angle in the order of 140 degrees or more, as the ship keeps plowing ahead. So when all is said and done, you're not getting a line of soundings along the ship track, you're getting a whole swath of soundings along the ship track, a much more efficient way to map the shape of the seafloor. And there is such a device in Melville, and Forsyth is making heavy use of that. Next was a transit from Valparaiso all the way around Cape Horn and into Cape Town in South Africa. This is a nomenclature for a leg on which there isn't any onboard scientific party. There may still be some scientific observations being made. Things like the multi-beam sonar may be operated just in the background as the ship is going from A to B, but it turned out that there was no specific scientific project that was going to make use of this piece of track, and all the rest of the next parts of the expedition, as you'll see, took place in the South African region, so it was necessary to transit the ship around and over. That doesn't mean that there aren't interesting things to see and to watch out for as you go. This is the ship rounding Cape Horn. That is Cape Horn right there on a balmy summer's day in the southern hemisphere. But even on balmy summer's days in the southern hemisphere, you run into creatures like this. This is one of well over 100 icebergs that the ship had to thread through to get around and into South Africa. This one is about 200 feet tall and 1,400 feet long. Not by any means the biggest one they saw. There was another one that was well over a mile long. And of course, these are the ones you can see readily. It's the ones you don't see so well are the guys that are likely to get you. So ice navigation was, an important part of this seemingly dull transit leg. Once the ship was over in Cape Town, the next piece of the operation was Deirdre Byrne from the University of Maine, looking into the physical oceanography of an aspect of the ocean circulation that occurs off this coast. There's a major ocean current called the Agulhas Current that comes down this coast of South Africa, where my pointer is moving now, and most of it typically turns and flows to the east along with the general scheme of currents in the far south. But occasionally bits of it will spin off in the form of isolated eddies or rings and wander their way into the South Atlantic, and she was looking at some of those processes. Next up was Henry Dick from Woods Hole, entirely different emphasis, looking at the structure and geochemistry of this piece of the Southeast Indian Ridge down here, and in particular, utilizing what's called the dredge to bring up rock samples from that ridge for subsequent analysis back ashore. It's kind of a square-shaped plow with a chain bridle on it here, and a big bag of chain behind it to capture up whatever it is you scoop off the sea floor. It's meant for capturing hard rocks, not mud. And it's again a specialized operation that really requires a capable research vessel to do it. The tensions on the winch wire in this kind of operation can get very high, and people who do this really have to know what they're about, or something can break and somebody can get seriously hurt. Lisa Beal, postdoctoral student here before she went to a regular position at the Rosenstiel School at the University of Miami, had the ship next, working in that Agulhas Current region that I pointed out earlier, up this eastern side of South Africa. Again, physical oceanographic work on the structure and dynamics of that current. And then another change of subject and discipline. Neil Slowey from Texas A&M took the ship up this western side doing sediment coring off the coast of South Africa and Namibia. I'll show you a little bit about how coring works in a second. It's worth noting at this point that this is one of two places in this circumnavigation expedition where geopolitics intruded. Slowey had been intending to do a lot of this coring work off the coast of Angola up here, and we had put in all the relevant paperwork to do that way ahead of time as required. But in the end, it didn't come to pass, and more or less in real time, we and Slowey had to alter his plan and do all his work in the regions that were not in Angolan waters. He may not be aware of the fact that the way the world is wired up nowadays, coastal states have the right to grant permission for scientific research within their so-called extended economic zones, generally speaking 200 miles off their coast. And in the case of Angola, it was either snarled up in the bureaucracy and or they didn't want to say no, but they didn't say yes. It's quite unclear how that worked out. The U.S. Embassy in Angola worked hard to try to get it sorted out, but in the end it didn't fly, and so that part of the operation simply didn't happen. This is a cartoon of how a sediment corer works. The apparatus is lowered from the ship on a cable, on a winch, and the first thing that hits the bottom is this little bitty corer, which also acts as a tripwire for this lever arm up here, releases it, and then the main event is that this big piston corer, driven by these heavy weights on its top end, plummets into the mud down below, and this little red job here, which is the actual piston, rides up in the core as the core barrel is shoved down into the mud, and then you extract the whole thing. This is when the tensions on the winch get really high and bad things happen if people don't know exactly what they're doing. But if it works well, you come up with a core barrel all full of a layered sample of the sediments, which is what you're trying to get at for geochemical analyses later on back in the lab. Here's a picture of the actual rig itself. There's the weights up there at that end. This is the coring pipe right here. Looks a little bit bent in this foreshortened view, but it is stiff enough that if things work right, it'll drive it right down into the mud, and you'll come back with a long tube full of mud like this that makes the geochemist just happy as clams. Next up was Donna Blackman from Scripps and Mark Oman from Scripps on this long passage across the Indian Ocean. Two completely different scientific objectives. Donna was looking at acoustic transmission properties along this path as part and parcel of ocean acoustic usage in nuclear test monitoring. Mark Oman's a biologist, and he and one of his students were working on capturing samples of particular copepods in this part of the world where hardly any samples exist. It may sound strange to think that we don't know who lives where in the ocean in a biological sense, but there's a lot of biogeography, I should say, particularly in remote areas that research vessels don't get to very often, that's still very much yet to be done. And so Oman capitalized on the fact that the ship was going to be going along this route and grafted on some sampling for these copepods while Donna was doing her acoustic thing, and it all worked very well. The ship came into Australia, and this was the second intrusion of geopolitics into the expedition. Originally, the ship had been going to go to Singapore for a port call, and subsequent to that, the plan had been to do some oceanographic work up here off the coast of Vietnam, looking at coastal circulations in this part of the world for Ken Brink from Woods Hole. Again, the appropriate clearance documents and inputs were made in timely fashion, but once again, even though the scientists on both sides, Vietnamese and American, were anxious to see this project succeed, permission was not forthcoming for whatever reason. You can speculate as you wish, and the whole plan had to be changed kind of at the 11th hour, and Ken Brink ended up doing a rather different coastal circulation study along the northwest shelf of Australia. I suppose the piece of good news in this is that the business of not going into Singapore took place at about the same time that there was concern about the SARS epidemic in Singapore. So from a public health perspective, it might have been a good thing that the change took place, but from the point of view of a place to make a port call, not to mention the original scientific plan, with all due respect to any Australians who are in the room, Port Hedland is not nearly as nice a place as Singapore. Anyway, Ken got something out of it with his work on the northwest shelf of Australia, and geopolitics tried to thwart us but didn't succeed entirely. That was followed by Coast Guard inspection in Darwin. There are required intervals for Coast Guard inspection for all these big ships, and sometimes they take place when it's handy here in San Diego, and sometimes they don't. And when they don't, we have to arrange to get the Coast Guard inspection team out there and send our own people out there to oversee things, and generally speaking, it goes okay. And it did in this case. Dave Nahr from the University of South Florida then took the ship to transit from Darwin around to Cairns, Australia, to install a shallow water multibeam, a much smaller rig than the big multibeam sonar built into the hull that I showed you before, and intended for use in shallower water. Operates at a much higher acoustic frequency because you don't need the lower acoustic frequency to propagate sound all the way down to the bottom of the ocean. Therefore, the physical apparatus, the acoustic transducers, can be much smaller, and the whole thing can be arranged on a device that you can clamp on the side of the ship rather than having to build it entirely into lots of feet of the hull of the ship. So Dave took advantage of this passage to get that shallow water multibeam up and running prior to the next leg that's coming up. And the Australian Navy, which was interested in perhaps obtaining another multibeam of the same stripe, was anxious to see how it worked and boarded the ship for some trials of that rig off their acoustic test range off of Cairns. And that's what took the ship for this period of time. Then there was a fairly large project involving a number of investigators, a few of whom are listed here, to the Fly River Delta on the southern side of Papua New Guinea, to look at a whole series of questions in geology and geochemistry to do with the Fly River Delta, how it's constructed. The river brings down enormous loads of organic debris and detritus into the continental shelf, and there it settles out and forms sediments, and there's all kinds of complicated geochemical processes going on that transform the sediments over time. And that was the sort of theme of this effort at this time, with quite a number of investigators from a number of different institutions involved. They also wanted to do it in a couple of different seasons of the year, because the input of sediment from the river system into the delta and on out over the continental shelf is seasonally dependent on the rainfall fundamentally, and therefore the river flow. So this was a big deal. It took a fair amount of time. They did the first portion of it, the first phase of the program, here in the August to October time frame, after which we had some downtime, and it was time for a shipyard overhaul anyway, so the ship transited around the corner here to Brisbane. We put her in the shipyard in Australia and did various kinds of ordinary maintenance and upgrades to the ship at that stage of the game. Again, it's a little bit of a coordination exercise to do something like that so far away from home, but with a proper amount of planning and a good shipyard, it can be done. And we've done things like this previously in Japan and elsewhere as needed. We'd prefer to do it back home, but if the schedules don't work out that way, we're prepared to do it elsewhere. Then came the second part of the Fly River Papua New Guinea exercise, and that was followed by a transit from Australia up to Yokohama, Japan, to get ready for the grand finale of this round the world tour. You can see we're closing the red line here fairly soon. Shazam. This was Jim Swift from Scripps from Yokohama back home to San Diego. He actually got in here one day earlier, the 27th. On looking at physical oceanography along this whole transect, temperature and salinity structure of the ocean, and a number of other chemical constituents of the ocean to do, among other things, with the ocean carbon cycle. Quite a long list of chemicals for which the seawater samples were analyzed, and I won't go into all of that, but suffice it to say that the ocean is a huge reservoir of carbon in the planetary system. There's, I don't know, 50-odd times as much carbon in the deep ocean as there is in the atmosphere. So when you want to talk about, are we mucking around with the carbon dioxide content of the atmosphere, and what does that mean? You have to realize that in the planetary system as a whole, there's this other humongous reservoir of carbon down there in the deep ocean, and detecting subtle changes in it may well be as important as detecting changes in the atmosphere from the point of view of understanding how the entire system is working. They're not decoupled. They do interact with each other at some level. So that was the nature of this part of the enterprise. The basic tool for all of this was about 150 lowerings of this CTD, conductivity temperature device. The reason for 150 stations I'll mention in a moment, but the device is shown here. Inside this ring of white sampling bottles where you can't see it is the package of electronic sensors for temperature and seawater conductivity, which is basically related to the salinity of the seawater. Those are the two key things you're trying to get at with the electronic devices. And also dissolved oxygen content in the seawater. And then at various depths as the device is being lowered, these sample bottles are given a signal down the conducting cable that closes their end caps, capturing a sample of seawater from whatever depth that was, to bring it back onto the ship for subsequent analysis in the laboratory or whatever you please, all kinds of different chemical constituents that are of interest to various members of the scientific party. The reason for 150 of these lowerings along that track from Yokohama to San Diego is that you're trying to sample the ocean at an interval that's commensurate with the variability in the ocean eddies and fronts that are just a commonplace there in the same way that frontal systems are a commonplace in the atmosphere. You wouldn't learn much about the storm systems and fronts in the atmosphere if you only had meteorological stations at, say, Kansas City and New York or something like that. You've got to have them a little more frequently across the country to build a picture that's worth looking at. And the same is true in the ocean. Given the scale of the kinds of things that are out there, you need to take these stations fairly frequently as you go along to get a useful picture of the variability in the properties that you're measuring, temperature, salinity, and all these chemical constituents. So I think that's it. We got the ship back to San Diego after 2 years and change. As I said, the longest time ever away from San Diego for a Scripps vessel. Terrific variety of scientific programs on the ship at different stages of the track. And I've told you all of this just to underscore the versatility, if you will, that these research vessels have to offer to be able to bring on the particular project and support it well, and then change the whole thing out at the next port and bring on the next group and keep on going. A little change of pace. UNOLS has been mentioned, University National Oceanographic Laboratory System. It's fundamentally a confederation or consortium of oceanographic institutions. They're sketched here on a map. The red ones are the ones that actually operate UNOLS vessels. So here we are, Scripps in San Diego, where we operate more UNOLS vessels than any other member of this consortium, 4. And here's the University of Washington, for example, and the University of Hawaii, and on and on. And the yellow institutions are members of UNOLS with marine science programs and people, generally speaking, that want to use research vessels for the research, but they don't actually operate vessels themselves. And there's 40-odd of those, I believe. You can think of it as the UNOLS organization is sitting at a kind of a funny crossroads between the member institutions, of which Scripps is one of the founding members, the ships of the UNOLS fleet that are scattered around the country at those red places that I showed you, and the federal agencies that pay the bills, whether by building ships and or paying for their operations in the course of time. The primary ones in that regard are the National Science Foundation, that turns out to be the heavy hitter with regard to costs of operating the ships, and the Navy, the Office of Naval Research, which turns out to have been the heavy hitter over time in terms of the funding, capital funding to build ships. And then these others are, as you see in their logos, somewhat smaller contributors to the whole. This is a kind of a busy slide. I apologize for it, but I think it contains some useful information. This is all the UNOLS vessels in the system that are bigger than 40 meters long. They're listed in order of the date at which they should theoretically retire, not necessarily that they're going to rust through and sink at that time, but that this would be getting to about the time when scientific obsolescence and increased frequency of machinery casualties and so forth would probably make it advisable to think about a replacement ship. They're color-coded according to who owns them. The blue ones are owned by the National Science Foundation. The red ones are owned by the Navy. So here's the Revell and Melville in our case. And the green ones are not owned by the feds at all. They're owned by states or universities, what have you. And they're grouped, the names are written down in terms of size. The big ones, the global scale vessels, so-called ocean class or intermediate size vessels, and regional ones here, like New Horizon, one of ours, for example. These are the vessels for which the feds have at least articulated some sort of a plan to maybe replace them some fine day if they ever get the money organized. At the moment, that is primarily a paper plan. There's a little bit of action at the National Science Foundation to try to accumulate funds to rebuild some of the vessels in the smaller size class, but I think it's fair to say that right now the outlook for really tackling the retirement problem that's posed by some of these numbers over here is clouded. There's nothing really super hard on the table that all of federal Washington has signed up to and said, we're going to do it, and found the money and put it on the table to do it. So I think the jury is still out as to how quickly this system is going to be able to cope with these indicated retirements of vessels. And we may well face a period of time in which some of these vessels are going to have to get scotch tape, baling wire, and Band-Aids and limp along for a few more years with all that that implies, just because the system will not have come up to speed with regard to the funding implications for recapitalizing this fleet. Some of us have been whining about this for a number of years, but our impact has been limited to date, I think I should say. These are the other vessels in the UNOLS fleet that are smaller than 40 meters, and the feds in their paper plan have said nothing about using federal money to recapitalize any of these, essentially throwing this whole problem over the wall to the non-federal sector, the institutions or the states, for good reason. As you can see, there's only one of these that's actually owned by the federal entity, the National Science Foundation. The rest of them are all owned by institutions, universities, and what have you. That's all fine and dandy, provided the institutions and universities can come up with the wherewithal to, again, tackle some of the near-term retirement problems that are coming down the road. But knowing something about the University of California's budget at this stage of the game, I wouldn't want to bet the farm on the idea that some of these things are going to happen, at least in our own context, anytime soon. So I think there is a significant issue out there about when, where, and to what degree the country is going to be able to step up and really rebuild this fleet at a rate commensurate with the fact that some of these vessels are getting old and long in the tooth. It's unfortunate, but I think it's true, and that's why I bothered to present these two slides to you. Give you some sense of scale for this whole UNOLS fleet operation with a couple of pictures here. This is the list of which agencies, NSF, Navy, yada, funded how much of the total pie for operation of the vessels, not building them, but operating them, in the period 1996 to 2000. So you see NSF is good for some 55% of the total operating cost, Navy for 19%, NOAA for 9%, and non-federal stuff, states, municipalities, institutions, various other sources for the remaining 14 or so percent. So it's a mixed funding source for the use of the ships. This is a little bit dated, it only runs to 2000, but the proportions have not changed radically since then. In aggregate, the fleet at this juncture was operating something like 4,900 days of ship use per year, all the ships in the UNOLS fleet, at a cost of just under $50 million per year for the operation. Again, that's paying for the crew and the fuel and the food and the insurance and the maintenance and the repairs and the whole 9 yards. Is that expensive? Depends on your point of view, I suppose. Here's a metric, not the only possible metric, but as I said earlier, these are kind of like the oceanographer's equivalent of manned space shuttles. There are shuttles that take our people and experiments to inner space instead of outer space. So if you want to look at NASA shuttle operations, this is previous to the Columbia disaster. They were running something like 7 or 8 flights a year at 10 days or so per flight, so there's a factor of a 60th there in terms of days of use. And that price tag was something like $3 billion, so there's a factor of 60 there, so multiply those two together and it's something like a cost factor of 3,600 between the UNOLS fleet on the one hand and NASA shuttle operations on the other hand. You know, I don't know if that's a meaningful comparison or not, you be the judge, but it's certainly the case that this operation here is minute by comparison. This was a report It was generated by NSF as it indicates the new millennium, or the turn of the millennium, published eventually in 2001. It was a fairly extensive review and projection across the ocean sciences by each of the disciplines in ocean sciences, with hundreds of inputs from scientists around the country, and followed by a sort of an overview and synthesis volume trying to put the whole thing together. And the bottom line that I want to cut to is the recommendation number 1 in this report, which says maintaining a modern, well-equipped research fleet is the most basic requirement for a healthy and vigorous research program in the ocean sciences. I've taken the liberty of underlining the, but the rest is a quote. And I think that really, for me, tells it all. It really is the case that these ships are the cornerstone of how we need to go about observing and continuing to observe the ocean. There is an issue as to how well that's going to be sustained in our national system down the road. The need now is for the government to grasp this nettle and figure out how to program money and so forth to take a serious crack at the rebuilding problem that confronts us. But there's no getting around the fact that ships like these are going to be needed for as far down the road as at least I'm capable of looking. So I think I'll close more or less as I began. I hope I've convinced you that the research vessels really are our equivalent of telescopes, the fundamental tool that we have for doing our business, and that even in this era of satellites and all sorts of other novel unattended instruments, which fortunately is advancing rapidly and greatly enlarging our means of looking at the ocean, there are still measurements that have to be done out there and scientific problems that have to be tackled out there that can only be done when we have capable ships that can take capable scientists and their instruments out to sea. And with that, I'll thank you very much and take any questions you may have. How is the budget for the coming year? Bleak. Not good. It's a struggle that we're going through right now. There's certainly going to be some retrenchment of ship operations, probably some ships idle for periods of time. I don't know yet whether any of the ships, either here or elsewhere, are going to be literally laid up for the entire year, but fundamentally it's a shortfall in money to operate the ships. There are scientific projects stacked up that would like to use the ships if somebody would give them the green light and the wherewithal to buy the ship time, but it's not particularly wonderful for the year 2006, and nobody that I've heard is predicting any rapid turnaround in '07 and beyond. What would I like to see in a ship of the future, assuming that the feds get around to building it? The first and foremost thing, I think, is a good seaworthy ship that's capable of a variety of oceanographic operations. And I think, I didn't mention this in the talk, but UNOLS has done already a tremendous amount of homework in conjunction with the NSF and the Navy looking at that question, and there's documents yay thick sitting on the UNOLS website about what should be the attributes of the next groups of vessels that we're going to build. And they get back to basics of seaworthiness and ease of handling a variety of instruments over the side. I would have to say that I think cost effectiveness is a big driver, and it's going to be more so. And that in turn translates into trying to keep the size of the crew as small as you can and still operate the vessel safely, because 50% or so of the cost of running the ships is the cost of paying the people. There are issues of acoustic quietness, so that more and more acoustic sensors can operate successfully on the vessel. I don't know that that involves radical new departures in technology, but it does involve reorganization of thinking in shipbuilding, so that that issue of noise control gets into the front end of a ship design and isn't a sort of a band-aid afterwards, because at that point it's too late. We've had some horrendous noise problems, not so much noise in the water problems, but noise inside the ship problems on the Ravel after delivery that took a fair amount of beating to get them civilized, in part because the approach of the shipbuilders has been to treat that as somewhat of a frill and not cope with it at a fundamental level. I think that inevitably the ships are going to become more and more connected to the digital world. It's already the case, as I indicated, where there's almost continuous connectivity to the internet from sea. That, I think, doesn't impose a tremendous problem one way or the other for ship design. You still want the seaworthy vessel. It's largely a second-order question of networking within the ship and appropriate antennas and places for them outside that they can talk to satellites or whoever. But I don't see it as a first-order ship design issue. And beyond that, it's the provision of habitability aspects that keep the ship as pleasant and comfortable as it can within the confines of a reasonably sized vessel. I mean, it's certainly the case that bigger is better. You know, if you want to build a really stable ship, you go build an aircraft carrier. It works just fine, but we can't afford that kind of thing. So inside of 250 feet or whatever it is, you want to work on the problem of keeping it comfortable as much as possible. Yes? The question is, why isn't a submarine the perfect research vessel for the future? Well, I can think of a number of, first of all, a crew of 200 would break our budget, okay? We got to get down to, we got to divide by 10 at least to make this thing work in our life.
I said they were there, not the
But it is an interesting question of what it would take to properly crew a submarine. I mean, I admit that you don't need all 200, but you may well need more than 20. If you're talking about a nuclear submarine, I think all bets are off. I mean, there's just no way that we're equipped to handle it. It's pretty tough to do measurements that involve things with the atmosphere from a submarine, at least to do it comfortably. And that's a chunk of what these ships need to be able to do, is meteorological measurements as well as straight oceanographic ones. And if you look at some of the size and unwieldiness of that hardware that I illustrated, and the kinds of pulling power that's required to yank a core sample out of the mud and things like that, you know, there's tens of thousands of pounds of tension involved in those exercises, and I would guess, although I'm not a submariner myself, that the ballasting might get a little weird under those circumstances. But it's an interesting idea. There have certainly been occasions on which submarines have been used for oceanography, and very effectively. There was a recent program within the last handful of years to do some ride-along oceanography on submarines going up under the ice in the Arctic, and there's a place where submarine really is a good thing because, you know, it's either that or an icebreaker. Take your pick.
Well, thank you very much, Bob. I'm sure I'll be glad to answer some questions afterwards.
Sure.
Thank you all for coming.